So let's solve problem number 8 of Stanford Math Tournament. The problem says what? Compute the remainder when this number is divided by 2020. Since I want that this video be useful for basic level students up to professional level math solvers, so it has 8 parts. I explain all these things, but maybe you know some of them, so you can use time codes or time steps in the description below. If you know, for example, permutation, combination, binomial expansion, all of them, only you don't know, for example, Euler's theorem, solve the problem, you can go straight forward to part 7, read and see Euler's theorem is what, and then to part 8, solve the problem. Or if you know all of them, you can go straight forward to part 8, solve the problem. So if you are new here, consider subscribing at any point during the video. Okay, we are gonna jump into part 1 right now. In this channel, we do a lot of problems of Stanford, Harvard, MIT, other Olympiad problems, just like this one. So let's start. Permutation is what? Permutation means arrangement. So, for example, if you have 1, 2, how many arrangement you have? Or a permutation, you say 1, 2, 2, 1. So you have 2 permutation. If you have 1, 2, 3, how many permutation do we have? 1, 3, 2. The first one, 2, 2, 1, 3, 2, 3, 1, and the last one will be what? 3, 1, 2, and 3, 2, 1. So 6 elements. How we can calculate? You say, okay, for example, here we have 2 elements. So you say what? You say 2 elements, 2 circles. The first one is 1, 2. The second one can be 1, 2. The first one you select. One of them 2, for example, you selected 1. The next one you can't select that element again. So for example, if you select 1, you select 2. If you select 2, you select 1 then. So here 2 times 1, 2. For 3 elements, you say, okay, I have 3 elements. Each of them can be 1, 2, 3, 1, 2, 3, 1, 2, 3. And then we say what? Here we have 3 elements. And for example, you select 2, then you have 2 elements because one of them you've selected. And at the end, we have 1. So 3 times 2 times 1 will be what? Will be 6, as we've reached here. But there is a sign, you say, okay, it's 3 factorial. You call this one 2 factorial. You define this sign. So if you have n times n minus 1 times 2 times 1, it will be what? Yes, n factorial. So permutation finished. Now let's jump into part 2. Part 2 is combination. It means what? Sometimes you have some elements, for example, like what your main set is 1, 1, 2, 3, 4. Problem, how many subsets are there with 0 elements? So it's what? 1 element only, 1. Part B with 1 element. So here it's easy. You can count. You say, okay, I have 1 element only. It can be 1, 2, 3, 4. So I have 4 cases. Part C will be a little harder and we want to learn the idea. Element. So you say what? You say, okay, I should select 2 elements. The elements are what? Each of them 1, 2, 3, 4. 1, 2, 3, 4. And then we say what? The first element has 4 cases times. The second element, for example, if you select 2 here, you can't select 2. And it will be what? 1, 2, 3. So you say the answer is 4 times 3, 12. But if I write all cases, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. If we count 1, 2, 3, 4, 5, 6, but here the answer is 12. Why this happens? Think a little by yourself, try. Okay, yes, exactly. if you consider, you select, for example, 2, 3, and also in some case you select 3 and then 2. So here we've crossed it because we've selected 2. If you select 3, you can't select 3. In this case, you can select 2. So 2, 3, 3, 2. But in subsets, 1, 2 is equal to 2, 1. They are same when you have set. So here we should divide by what? Divide by permutation or arrangement of each subset. If we use part 1, we should divide it by 2 factorial because each two elements have 2 factorial arrangement or 2. If we divide by 2 factorial, it will be what? It will be 6. Now, let's generalize this idea. In part D, you say by 3 elements here. If we have 3 elements. So here you say I have 3 elements. Okay, so the first one can be 1, 2, 3, 4. The second element can be 1, 2, 3, 4. The last element also can be 1, 2, 3, 4. So 4 cases you have here times. You selected one of them, you can't select that anymore, so it will be 3 times 2. So it will be 4 times 3 times 2. But we should divide by what? We consider 1, 2, 3. We calculate this also 1, 3, 2. We calculate all permutation of these 3 elements. So we should divide by 3 factorial like part 1. And if we want to simplify, let's see, it will be what? 4 times 3 times 2. 3 factorial will be 3 times 2 times 1. So 3, 3, 2, 2, it will be 4. Now, let's check. If we want to see how many subsets with 3 elements are there, you say 1, 2, 3. You don't select 4. 1, 2, 4. You don't select 3. 1, 3, 4. You don't select 2. And 2, 3, 4. Exactly. We have 4 subsets with 3 elements. And the last one, you say, okay, E with 4 elements we want to select. Okay, if you want to select with 4 elements, again, we say, okay, we have 4 places. Similarly, you say, okay, the first one can be 1, 2, 3, 4. This one, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So you say 4 times 3 times 2 times 1, which will be, you can write also it is 4 factorial by the definition in part 1. Over each subset, for example, 1, 2, 3, 4, you calculate all the permutation over 4 factorial. Because 4 factorial permutation, it is 1, and it's obvious. Because the only subsets with 4 elements, our main subset is 1, 2, 3, 4. So the only subset with 4 elements is exactly itself. 1, 2, 3, 4. So let me tell you a definition, a symbol you can show. You say, okay, 4 choose 0 was what? Part A. The number of subsets with 0 element. It was what? It was what? Only null set. It was 1. 4 choose 1 was, they show like this. They say what? 4 choose 1. It means what? Number of subsets of 1 to 4 with 1 element. So we said it was what? It was 4. 4 choose 2 is what? Was number of subsets of 1 to 3, 4. You want to select 2 elements. It was what? 4 times 3 over 2. So this formula you can generalize. If you have, for example, n choose 2, you say, okay, number of subsets with 2 elements from 1 to n. The first element, n times n minus 1 over 2 factorial. And it was what? We've calculated 6. Also, you can say 4 choose 3 was what? 4 times 3 times 2 over 3 factorial. You can say n choose 3 is what? N times n minus 1 times n minus 2 over 3 factorial. Okay, you can write this. Also, it has other formulas, but I wanted to only explain for you. You say something, choose something, and let me tell you, n choose 1 will be n choose 1 means you have n elements, number of subsets with one element. It will be n, and n choose 0 always is what? You have 1 to n number of subsets with 0 element. It will be what? It will be 1 null set. Okay, now we are ready to go to part 2. Sorry, part 3. Binomial expansion is what? For example, you say x plus y to the power of 1, x plus y squared, x plus y to the power of 3, x plus y to the power of 4, for example, like so on. We want to see how we can find a formula to know there are what. So the first one is obvious, x plus y. The second one, you say x plus y times x plus y. So you say for x squared, you have only one way to select x, x. For next one, for xy, you can select xy, yx. So it will be xy plus xy, 2xy. And for y squared, you should select y from both parts. So it will be plus y squared. Now let's calculate third one. You have x plus y cubed, x plus y, x plus y, x plus y. So for x cubed, it's easy. You say I should select x from all sides. If you want to find the coefficient of x squared y, you say, okay, I should select from two parts x and from other part y. So here you have three parts. You want to select two of them. Select two of them for x. So how we can say? You say these two, these two, these two. So do you agree if instead of 3 we had 8 and we wanted to select 3, it was hard to calculate? Exactly. So we can use part 2. In part 2, we can say, okay, you have 3 parts. You want to select two of them for x. So it was what? 3, choose 2. For example, it is first, second, third. You want to select two of them, subsets with two elements. 1, 2, 1, 3, 2, 3. So you can write 2, 3, choose 2. Okay, so let me write it a little better. Yes, 3, choose 2. xy 3, choose 2 is what? By the formula we've calculated in part 2. I said 3, choose 2. N choose 2 is always 3 times 2 over 2, which will be over or 2 factorial, which is 3. And plus what? The next one, you say xy squared. Again, you want to select 1x, you say 3, choose 1. Maybe you say, okay, when you select x, after that you should select y. I say, okay, but selecting y will be unique. Why? Because, for example, you want to select 1x, 2y. So you select this x. Now selecting y will be 2, choose 2. Unique. You should select from other parts only y. And the last part is what? Is y cubed. Okay? Y cubed, it's unique. You should select these three y's. But if I want to generalize and find the formula, it will be what? You can say 3 choose 3, x cubed plus 3 choose 2, x squared y plus 3 choose 1, xy squared plus 3 choose 0, y cubed. So maybe some of you says, okay, instead of 3 choose 2, we select 2 for x's. Maybe I want to write 3 choose 1 for selecting y here. I say no problem. 3 choose 2 you can prove easily by the formula I told you is always equal to 3 choose 1. Here instead of 3 choose 3 you say 3 choose 0. So it is always 3. 3 choose 3 equal to 3 choose 0 equal to 1. So it is not important you consider selecting x or selecting y. Now I want to generalize this one. I will tell you this one for 4. For 4 it will be what? Can you guess? x4, you say okay, 4 choose 4 plus 4 choose 3 x cubed y plus 4 choose 2 x squared y squared, decrease the power of x, increase power of y by 1. 4 choose 1 x y cubed, and the last one is 4 choose 0 y 4. Now if I want to generalize this for n, it will be what? It will be x plus y to the power of n equal to n choose n x to the power of n plus n choose n minus 1 x to the power of n minus 1 y plus n choose n minus 2 x to the power of n minus 2 y. And you can write until, for example, n choose 2, you have x squared y plus n choose 1 1x, you select x y n minus 1, and n choose n y to the power of n. And the proof is not hard, because for example for this one you say okay, you select n minus 1x from these n parts. So here you say okay, I have 1 2 and I want to select n minus 1 for x, so it will be n minus n choose n minus 1, and the last part you should select y from that. Okay, so let's jump into the part 4, congruence properties. So congruence is what, or modulo. So for example, you say what A is congruent to B, they write like this, mod for example M. It means what? For example, look, when A and B have same remainders when divided by M. For example, 4 is congruent to 2 mod 2. It means what? 4 and 2 have same remainder when divided by 2. Both of them have what remainder? Have 0. They are even numbers. Or you can say, for example, 5 is congruent to 9 mod 2, because both of them are odd and the remainder when divided by 2 is 1. So this definition you can write, and it has some properties. For example, one of them is what? You say okay, for even numbers, for example, if I want to write, I can write all of them. I say what? I say okay, if I write 2, then I can write, for example, 0. All of them have same remainder when divided by 2. So you can add 2. 2 plus 2, 4. It is again even. 2 plus 4, 6. And so on. So when you have mod 2, you can add or subtract by 2. Negative 2, negative 4, and so on. So here all of them have same remainder. Let's solve for example, also 1. When we have all mod 3, you can use mod any natural numbers or positive integer. 1 plus 3, 4. 3 plus 4, 7. 3 plus 7, 10. So on. And 1 minus 3, negative 2, negative 5. All of them have same remainders. And the other words they say, if something, for example, A is congruent to B mod n, for example, you can say it is equivalent that n is divides, or let's say this, A minus B is divisible by n, or you can say n divides their difference, A minus B. So let's check. Here, for example, you have negative 5 and 7. So their difference should be multiple of 3. Let's check. 7 minus 5 is 7, plus 5 equal to 12. 12 is multiple of 3. So the left side minus right side, or right side minus left side, their difference, their subtraction is always multiple of n. So these things were definition of congruence. And now we want to work on some rules. For example, when 2 is congruent, why? The symbol is similar to equality. Why? Because the idea is exactly similar to the works, the things, product and addition and subtraction is equal exactly to, similar to equality. Why? For example, look, you have 2 is congruent to, for example, what can we say, to 8 mod 6. Okay, 8 and 2, they have same remainder. You can add both sides by, for example, 3. both sides by same number, for example, any number, for example, by 7. And 8 plus 7. It will be 9, it will be what? 15. And both of them are congruent mod 6. They have same remainder, or 15 minus 9 is 6 multiple of 6. So here we can add, we can subtract, we can multiply. For dividing, so we work on like exactly equality. For dividing, let me tell you, for example, suppose you have AB is congruent to AC mod n. You want to divide A. It is not always correct. The only case that is not exactly similar to equality is when you want to divide. If you want to divide, let me tell you, you should do what? You should check that. Okay, by the definition we said AB minus AC is what is divisible by n, is divisible by n. But you can say, okay, A times B minus C is also divisible by n if A and D, let me write GCD of A and n is 1, means they are relatively prime numbers, they don't have any common factor. So do you agree when A times this number is multiple of n or divisible by n, if GCD of A and n equal to 1, then we can say, okay, A is not important, and we can conclude B minus C is divisible by n. And then we can say, okay, it means what? By the definition, B is congruent to C mod n. So if A and n are co-prime numbers, relatively prime numbers, then you can divide both sides by A. Let's say some example. You can see 2 times 5 is what? Is 10. 2 times 17 is what? 34. If you divide both of them by 3, then the remainder is 1. They are equal. And if we divide, so by 2, both sides. Why we can divide? Because GCD of 2 and 3 equal to 1 here. Okay, so 5 is congruent to 17, and if we check, we will see it's correct. But let's find something GCD is not 1. When GCD is not 1, it is not necessarily correct. Here, 2 times 5 is 10, 2 times 6 12, both of them even, they have same remainder when divided by 2, so they are congruent mod 2. If we divide both sides by 2, then 5 is congruent to 6 mod 2. Is it correct? No, the left side is odd, right side even. And their difference is not multiple of 2, or they don't have same remainder when divided by 2. So here it's not correct. So we've considered product. Also, it has many other rules. So let's solve some problems with congruency. Okay, it will be part 5, application of congruence. For example, someone says 2 to the power of 100 is what? Mod 7. It says what? It says when 2 to the power of 100, when divided by 7, the remainder is what? You can say what? You can say, okay, 2 squared is not good, 2 cubed is 8. 8 is what? 8 is equal to 1 or congruent to 1 mod 7. So here, if you multiply any 3 2's, it will be 1. So you say, okay, 2 to the power of 100, 2, 2, 2. The next part, 2, 2, 2. And you go until last part, 2, 2, 2, 99. And 1, 2 is left. So it is congruent to what? 1 equal to 1. This one equal to 1. This one equal to 1. Each of them. Because 2 cubed is congruent to 1. The remainder is 1. And then 2. So the answer is 2. So here we've done what? If I want to calculate, if I want to write it professionally, I can say 2 to the power of 100 equal to 2 cubed the power of 33. Like here, it is the first part, second part, third part times 99 times 2. And if you consider mod 7, it will be 833 times 2. And 8 is what? 133 times 2, which is 2 mod 7. So We can find many remainders of power of large numbers like this problem, the Stanford problem. You can use congruence. For second example, you want to find 11 to the power of 100 mod 9. Here we want to find the answer mod, and in general we will solve. So you say 11 is what? 11 equal to or is congruent to 2 mod 9. So you say what? 11 is 1, it's 2. So 11 to the power of 100 is congruent to 2 to the power of 100. So look, we want to find something like previous one, that it reached to 1. So 2 is not good. 2 squared is 4, is not so much good. 2 cubed is 8. It's good. Why? Because if you consider mod 9, you can add 9 or subtract 9 from this. If you subtract 1, it will be negative 1. So you can say it's good. 2 cubed, the power of 33 times 2, and it will be what? 8 to the power of 33 times 2 mod 9. It will be negative 1 to the power of 33 times 2. And if I want to write, it will be what? It will be congruent to negative 1 to the power of 33, negative 1 times 2. It will be negative 2 mod 9. You add 9, it will be 7. So here we found this. For this problem also, we want to use something like this. Now, the next application you should know is someone says the remainder of a when divided by 3 is 1. The remainder of a when divided by 5 is 2. Can you guess that we can find a is congruent? We can find the remainder when divided by what? We know 3 and 5. LCM of them exactly 15. And if you want to find this, one way you say, okay, 2 instead of 2 you can write also is congruent 5 plus 2, 7. Does 7 satisfy this? Yes, because 7 and 1 have same remainder, so it will be 7. So you should reach same number here, for example, by adding 5, by adding 3. One way is this. It has also other ways. And we can say always we have answer if these numbers are co-prime numbers. For example, here a is 1 congruent to 1 mod 3, remainder when divided by 5 is 3, remainder when divided by 7 is 2. You can sure that you can find a congruent to what remainder mod what LCM of these three numbers. LCM of them because they are relatively prime product. So here there is a theorem, Chinese remainder theorem. It says what? If, for example, 3 and 5, each two of them are relatively prime, and it has answer, we can find the answer. Chinese remainder theorem. So we don't need to prove that because then the video will be so much long, but it has answer. It's the famous theorem, and you can find the answer. I showed you how you can find the answer. For rest of the part, you can use exactly this idea to find the answer, and also if you don't need to use Chinese remainder theorem, but because this theorem is important, I want to just tell you in many sometimes other problems you can use that. Part 6, Euler's totient function. It is a what? Look, for example, consider the sign is this. Phi of, for example, 5. It means what? You should consider from 1 to n. 1, 2, 3, 4, 5. And see how many of them are relatively prime with 5. So 1, 2, 3, 4. 4 of them. So phi of 5 is 4. Let's consider, for example, phi of 6. You consider 1 to 6. And which of them are relatively prime with 6? Have no common factor with 6. 1. 2 is not. Also here 5 was not. 5 and 5. So 2 not. 3 not, because 3, 6, the GCD is 3. They are not relatively prime. 4 is not good. 5 is good. 6 is not good. It will be 1 plus 1, 2. For phi of 7, it will be what? If I write all 1 to 7, 1, 2, 3, 4, 5, 6, 7, it will be what? 1 is good, 2 good, 3 good. All of them are relatively prime. 5, 6, 7. It will be 6. So we guess for some numbers, 5, it was 5 minus 1, 4. For 7, it is 6. 7 minus 1. Can you guess phi of what number? Well, phi of n is n minus 1. It means what? It means n is relatively prime to all numbers less than that. For what numbers this happens? That number is relatively prime to all numbers less than that? Yes. If we consider phi of p, that p is prime, then we can say, okay. If we consider 1 to p, all of 1 to p minus 1 are relatively prime with that. For example, like what? Like 7. Phi of 11 is also what? Is 10, 1 to 10. For this problem, we need to find phi of 101 because 101 is prime, so phi of that is what? Exactly, 100. In this part, I wanted to only show you the things that we need. Phi, the definition of phi is what? Now, in next part, we will consider the application and the theorem we can use this phi. Euler's theorem says what? Says, for example, suppose 2 and 5 are relatively prime numbers. Their GCD is 1. And phi of 5 from previous part is what? It is prime number, so you say 4. It says, it is general theorem of Little Fermat's theorem. It says what? It says 2 to the power of phi of 5 is congruent to 1 mod 5. This theorem says this. So let's check. 2 to the power of phi of 5 is 4, is congruent to 1. Is it correct? So let's check. 2 to the power of 4 is 16, 16 and 1. Both of them have same remainder when divided by 5. So it's okay. Now, if I want to generalize it, GCD of A and N is 1. So we can say a to the power of phi of n is congruent to 1 mod n. So it is correct and it's so much useful. Euler's theorem, a to the power of phi of n is 1. It's so much useful. Now, I want to prove this. How? At first, let's check for example, some number like 5. So you write all the numbers. I want to consider mod 5. I want to prove at first this one for numbers, then for variables. If you consider mod 5, the numbers that are relatively prime to 5 are this. Now, if I multiply each of them by 2, 2 times 1, 2 times 2, 2 times 2, 2 times 3, 2 times 4. And we can check, if we check remainder of each of them when divided by 5, it will be 2 mod 5, 4, mod 5, 6 is what mod 5, 1, because you can subtract 5, 8 is what, 3. So look, it is exactly 1, 2, 3, 4, here 2, 4, 1, 3, same permutation. So I say what? I say, okay, 1, 2, 3, 4 is congruent to what? 2 times 1, because they are exactly this set. The numbers exactly 1, 2, 3, 4 with other permutations. So if you product, they will be same mod 5. Why? Because for example, this one is 3, this one is 1, this one is 4 here, by this one is 2. So 1, 2, 3, 4 equal to 2, 4, 1, 3. Product, in product it's not important to change the arrangement. Mod 5. And then we can say what? You can say, okay, it is 1 times 2 times 3 times 4 is congruent to, or you can write, let me write that first, 1, 2, 3, 4. I subtract all these parts, 1, 2, 3, 4, and times, I have 4 2's. 1, 2, 2, 2, 3, 2, 4 2's. 2 to the power of 4. And you can see what? You can see, okay, this part is 24, 24, and by part, I think 2 or 3, I've checked, by part 4, I said when 24, you have 24, 24, you want to divide by 24. Since GCD of 24 and 5 is 1, you can divide both sides by 24. Okay, so if you divide both sides by 24, 1 is congruent to 2 to the 4 mod 5, and it's 2 to the power of phi of n. So if you want to generalize this for variables, it is exactly the same. You say a1, a2, to a phi of n. We have these numbers. They are relatively prime. AI and n are 1. Now we said a and n is 1. The problem is prove Euler's theorem a to the phi of n is 1 mod n. So how we can prove that? I multiply each of them by a. AA1, AA2, and AA phi of n. And we want to prove that these numbers, if we consider mod n, they are same numbers mod and only the arrangement has changed. Okay, so how I can prove this? I want to prove each of them are different when divided by n. They are not congruent, so the number of them is phi of n. We have exactly phi of n numbers that are relatively prime with n, so these numbers are exactly a1 to a phi n when divided by n. So how can prove that? I want to say all of them are different, AA1. So for example, for AA1 and AA2, I prove if mod n they are congruent, I want to prove by contradiction that it cannot be happened, and it will be what? You say, okay, a and n are co-prime numbers, so you can divide by a both sides. So a1 is congruent to a2 mod n. It is contradiction because these numbers were from 1 to n, that they are co-prime with n, and all of them are different number of them. For example, for 5 you say 1, 2, 3, 4, all of them are different numbers. So here we have contradiction, and we conclude this, and then we product. You say a1 times a2 times to a phi of n is congruent to aa1 times aa2 times aa phi n. It is what? Mod n. And then we can conclude what? We say, okay, the first part is a1 times a2, exactly like for 5 we proved. For 5 we said what? Look, exactly like here. 1, 2, 3, 4 is 2, 1. It is aa1, aa2, aa3, aa phi n. And then we consider 1, 2, 3, 4 and 1, 2, 3, 4 and times 2 to the 4. We want to do exactly same thing. So it is congruent to a1. We consider only a1, a2 to a phi n to a phi n times how many a do we have if I want to write a1, 2 to a phi n, a to the power of phi n mod, and we know a1, the definition was this, a1 and n are co-prime numbers, a2 and a phi n, all of them, so you can divide both sides by this a1 to a phi n, it will be 1, you divide both sides by this a phi n mod n. So I proved Euler's theorem, and little Fermat's theorem is Euler's theorem only for prime numbers, and also by this proof you can prove little Fermat's theorem exactly by the same way. Okay, now we are ready to solve the problem part 8. Compute the remainder when this number is divided by 20. Okay, so let's solve this problem. If I want to write mod 2020, the first number, let me call this one a will congruent to what? Instead of 2018 mod 2020, I told you in previous parts, you can subtract 2020, it will be -2. So it will be -2 to the power of 2019 to the power of 2020 plus 2019 here. Similarly, you can say -1, 2020, 2021 plus 2020 is 0. It's good. 0 to the power of 2020 to the power of 2020 plus 2021 is 1. Why? Because you can subtract 2020 and it will be what? Mod 2020. So it will be 1 to the power of 2020, power of 2019, plus 2022 is 2 to the power of 2021 to the power of 2020. So if I want to consider congruency mod 2020, then it will be what here? The first one is what? -2, -1 to the power of what? 2019, odd number. So it will be -20 to the power of 2019 to the power of 2020. This -1 is to power of even number, so it will be +1. This 0 will be 0. 1 to power of anything will be 1. Plus 2 to the power of 2021 to the power of 2020. So now we should focus. It is what? Mod 2020. Now we should focus on finding this number and this number when divided by 2020. Okay, so as you remember, in one part I said when you have this number 2020, it's LCM of what numbers? If you prime factorize, it will be 2 squared times 5 times 101. And for example, I want to find 2 to the power of 2019 to the power of 2020 mod 2020. So instead of that, I can say, okay, a mod 4 is what? A mod, let me call this number A, small a mod, because it's for 4 instead of 2020. We can say mod 5 is what, if we calculate that. And a mod what? Mod 101 is what? If you know these things by the part application of congruence I've explained. If you know 4, 5, 100 mod this, you can find mod LCM of them, which is 2020. So it's easier 4, 5, and 101. So how we can find that? Mod 4 is easy because it is 2 to the power of large number. It is 0. If we want to find mod 5, so let's consider mod 5. It will be what? It will be 2 to the power of what? 2, 1 is not 2 power of 2 is not 2 to the power of 5. We know is 1 mod 5. Why? Because we said if 2 and 5 are relatively prime by Euler's theorem, in part of Euler's theorem, we can say this phi of 5 is what? Because it is prime 1 to 4 or co-prime, relatively prime with that 4. So 2 to the power of 4 is 16, is 1 mod 5. Now, here, each 4 2's you multiply will be 1. So if I find the remainder of this number when divided by 4, then I can say, okay, the remainder of this number, A, when divided by 5 is what? So I should find 2019, and in the rest you will understand why we've calculated mod 4. If you want to find mod 4, 2019 is -1. -1 to the power of 2020 is 1 plus 1. So we'll understand this number 2019 to the power of 2020 is the remainder when divided by 4 is 1. You can write 4 cubed plus 1. So here you can say 2 to the power of 4 cubed plus 1. And if you want to calculate, let me call it will be what? 4 cubed plus 1. We said the power is this. So it will be 2 to the power of 4 to the power of q times 2. 2 to the power of 4 is 16. 16 we said is 1 mod 5 is 1 to the power of q times 2 is congruent to 2. Now we do the same way for 101. We know what A is what. Let me write A again. A is this. We want to find remainder when divided by 101. Again, I use Euler's theorem that I told you in that part, Euler's theorem part. So I know that 2 to the power of phi of 101 is congruent to 1 mod 101. Phi of 101 is prime, and in previous part I found it. It is this minus 1. From 1 to 100, all of them are co-prime. 1 mod 101. So here, because I know 2 to the power of 100 is 1, I should understand that this number is 100 cubed plus what? Because each 100, 2 that you multiply by itself, it will be 1. So I should find the remainder of this number, 2019 to the power of 2020, when divided by 100, like previous part that we had. Okay, so let's calculate 2019 to the power of 2020 when divided by 100, because we don't have enough space. So let's find it here. Okay, so let's calculate this. I calculate this by binomial expansion. I explained this in the part binomial expansion, it is 2020 minus 1 to the power of 2020. I say what? It is negative 1, 2020. For example, choose 0, you don't select this, and you select negative 1 to the power of 2020 plus 2020, choose 1, negative 1 to the power of 2019 times 2020 to the power of 1, and the next part will be 2020, choose 2, negative 1 to the power of 2018, 2020 to the power of 2, and so on. So if you come on to consider mod 100, if you pay attention, this part from this part, all of them are 2020 to the power of 2, 2020 to the power of 3, all of them are multiple of 100. So if you consider also this part, 2020 choose 1, we said in combination part it is 2020 times 2020, it is also multiple of 100. 2020 choose 0 is 1, negative 1 to the power of this is 1, so it will be 1. Okay, so it is 100, for example, k, it is 100 k prime, so only it is 1, it is 1, so 1 times 1 is left. So we found 2019 to the power of 2020 is congruent to 1, so 2019 to the power of 2020, you can say is 100, for example, t plus 1, because it's congruent to 1 mod 100. So you can say what? You can say 2019 to the power of this is 1, and we can say what? If you want to calculate the mod 101, you say, okay, it is 2 to the power of 100 cubed plus 1. And we know 2 to the power of 100. Instead of q, I said it should be t. So let me write t here. We said not q because we've used q. Don't use same variable for different numbers in one solution. It will be what? We said 2 to the power of 100 is 1 because of Euler's theorem. Is 1 to the power of t times 2 is 2 mod 101. So we found this for this number for a, which a is what? A was this number. Now we should find what? It was a, and now I want to find b. Okay, if I want to calculate this, I want to calculate mod 2020. It is exactly similar. Instead of 2020, because you factorize, it will be 2 squared times 5 times 101. We want to find it mod 4, mod 5, and mod 101. So if we want to calculate this, so for the first part, similarly, you say, okay, it's 2 to the power of something, so it's 0 mod 4, exactly like previous part, 2 to the power of other numbers for small a. We've calculated for 5. Again, you say, okay, it's 2 to the power of 4 is 1 by Euler's theorem, exactly like previous part. And similarly, you say, okay, I should calculate this mod 4. And if you calculate this mod 4, it will be, this one is 1 mod 4, 1 2020 is congruent to 1 mod 4. So it will be what? It will be 2 4q plus 1, because the power is 1 mod 4. It is 4q plus 1. And because 2 to the 4 is 1, you can say 2 to the 4 q times 2 is congruent to 1 times 2 is congruent to 2. And for third part, mod 100, we said 2 to the power of, let me write it here with red, you say 2 to the power of 100, exactly like previous part. I consider it completely for small a. 2 to the power of 100 mod 101 by Euler's theorem is 1. So we should calculate this number mod 100, because we want to see it will be 2 to the power of 100, for example. Let me write q prime because I've used q for previous part. And this is t prime plus what? So I should find 2021 to the power of 2020 mod 100. And if we use binomial expansion, it will be exactly this to the power of 2020. And exactly if you write binomial expansion, it will be what? It will be 2020, choose 0, 1 to the power of 2020, and plus 2020, choose 1. I explained completely binomial expansion in previous part. This 2020, and plus the next part has 2020 to the power of 2, and all of them will be multiple of 100. 100, for example, r. So what is left? 1 times 1. So it will be this, and then you can say, okay, 2 to the 100 p prime times 2, it is 1, it will be congruent to 2. So as you can see, 0 to 2 for this number, and for previous number, if you check, it was also 0 mod 4 2 2. So this A and B will reach same number because both of them are 0 2 2 mod 4 5 and 101 respectively, because they are equal. So you can say A and B are equal because mod 4 mod 5 and mod 101 we prove they are equal. So because negative A and plus B, you can cancel this negative AB, and 1 plus 0 plus 1 is 2. So the answer of this problem is 2. I released many other videos for Stanford, Harvard, MIT Math Tournament. You can see them and improve your problem solving. And you can click on the link on the video on that you can see and use them. If you had any question, feel free to send message to my WhatsApp number in the description. Also, comment if you have any question. And thanks for watching my videos and for your support.